Okay, okay. So we were talking last time about sequences. So a sequence, of course, is a list of numbers written in an order, and the numbers are generated by a formula. And last time, we actually were able for the first sequence in A and the second sequence in B, we were able to find a formula for those two sequences. And naturally, that would be in the recording as well for section 8.1. So if you look either in Blackboard under recordings or the course content, uh, find section 8.1, the recording for the first lecture, next section 8.1 should be there. But now what we want to do is we want to look at this. So we did already formulas for A and B. We found formulas for those sequences. Now we're focused on the sequence for formula C. And it's an interesting sequence. The numbers go 5, 1, 5, 1, 5, 1, and just keep going and going and going. And but there is a sequence, a formula that generates those numbers. So let me go right to the solution here. Well, before I go there, we have to, of course, think about what is the formula. So this, I think, C is more difficult than A and B because the sequence is just oscillating back and forth between these values of 5 and 1. And incidentally, when we get the formula for the sequence, for this sequence, there can be other formulas too. Okay, formula for a sequence is not unique. There are multiple formulas for any given sequence. But we're always assuming that we're starting at n equals 1. So like for this problem, the first term is 5. The second term is 1, and so forth. Okay, so we're always assuming that we start with n equals 1. Okay, so let's go ahead and go to the solution here. And let's take a look at how it's worked out. So the first term is 5. The second term is 1. The third term's 5. The fourth term's 1. Okay, and what we can do is we can say that well, if we plot the sequence, as I've done here, like on the horizontal axis, we have the n value, okay, which is the number, which is the first term, second term, third term, fourth term, and so forth. On the vertical axis, we have the term itself, the nth term. So when n is 1, the term of the sequence, the first term is 5. When n is 2, the second term of the sequence is 1. When n is 3, the third term of the sequence is 5. When n is 4, the fourth term of the sequence is 1. So one thing that you could recognize is that the terms are oscillating back and forth about the 3. So in other words, 5 is 2 more than 3. Okay. The first term 5 is 2 more than 3. The second term 1 is 2 less than 3. The third term 5 is 2 more than 3. The fourth term, which is equal to 1, is 2 less than 3. So we could say that the general term of the sequence, well, I basically then mathematically write that down as you see here. for the terms of the sequence. And based off of that, the general term for the sequence, the nth term of the sequence, could be expressed as 3 plus 2 times -1 to the n plus first power, where n equals 1, 2, 3, and so forth. I mean, that would work. That would work. That formula would generate the sequence. But for this problem, it helped to actually plot the sequence. Okay, so let me give you a moment to copy that down. Okay, checking one thing here, one moment. Okay, let me see here. There was a question here. There are multiple answers. So like for instance, good question, Michael. So like for instance, the nth term could be expressed as 3 plus 2 times -1 to, well, instead of n plus 1 power, could we have a different power instead of n plus 1? So you see the power here, we used n plus 1. We use this power because, like for the first term here, we need to have a positive 2. So, well, all right, when n is 1, 1 plus 1 is 2, and -1 squared is a positive 1, so that gets you a positive power. However, the next term, the second term is 1, which is 3 minus 2. So we need to have this term here, -1 to the n plus 1 power. We need it to be a -1 for the second term. And when n is 2, you're going to get -1 to the third power, which is -1. So it works out. It works out. See, we have to adjust the powers so we get the right, plus and minus in the right spot. But if I didn't want to have a -1 to the n plus 1 power, could I have a different power there? Like, for instance, would n plus 3 work? If you were to type this formula in WebAssign. Okay, Rodrigo, says yes, it would. Because when n is 1, when n takes on odd values, this power here is going to be +1 when n takes on odd values, 1, 3, 5, 7, and so forth. Any odd number, well, that's right, and Colom's right. N plus any odd number would work. That's absolutely right. So you see, you can have multiple answers. Okay, multiple answers. Okay, are there any questions? Any questions at all? All right. Well, if there are no questions, then let us continue on in our section 8.1. So what I'm going to do is I'm going to stop the sharing on this one here, and we'll look at some more examples. So let me bring up some more. I have to bring them up. All right, it's coming up here. Loading. Just give it a moment here. Okay. Okay, so we're going to look here at some different sequences. We're going to actually look at 6 sequences. And we're going to ask if the sequences converge, or diverge. So when a sequence converges, that means as n gets large, the sequence approaches a number. Converge means to come together. Okay? So if a sequence converges, that means as n gets large, the sequence approaches a number. Okay? And if the sequence diverges, then the sequence as n gets large, as you look at terms in the sequence out toward, as n goes, the 100th term, the 1000th term, the 1,000,000th term, the terms as n gets large are not approaching a number. That's what diverge means in simple terms. Let me give you a moment to copy this, copy the different ones down here. Okay, one moment. Okay. All right. Okay. So I just want to, I'll mention real quick, not Nell, I think the assignments were fine. The 8.1 due Sunday was, I mean, I checked it. It looks okay. So I think, I don't know, and not Nell made a comment that the 8.1 was maybe not due on, was due Friday, but Sunday is November 1st, so it's okay. And 7.1 exercises, like the past due assignments, it's under past due. I think the extension is, I looked at it, it looks like it's till Wednesday at 2:55 p.m. So, but at any rate, uh, uh, look at it again when the time comes and let me know. I always appreciate students, help letting me know when things are possibly not right, in regards to due dates and stuff. So thank you for that. Okay, so again, we are looking at we're interested, like we learned about how to find formulas for some sequences. And in this problem, we are given different sequences, and we want to know if the sequences converge. And again, converge means that the sequence will eventually approach a number as n gets large. So let's look at the first one. Now, the first one, I mean, if we just intuitively sort of look at the sequence, okay, if we intuitively look at it, well, does the sequence in A oscillate? Is it an oscillating sequence? Meaning, going from negative to positive, or going from positive to negative. Is the sequence in A an oscillating sequence? It is. It is. Definitely it is. And if we look at the solution here for A, what I've done is I've written out some terms of the sequence. Okay, I've written out some terms of the sequence. I've written out here the first 5 terms of the sequence. So, negative 1/3, 2/5, negative 3/7, 4/9, negative 5/11. Are we okay? Are we okay with how I'm getting these terms? I mean, are there any questions on that? Like the first term, maybe I'll just mention it. I'll maybe sleep better if I do that. How did I get the first term there? Negative 1/3. Well, that's the first term. So when n is 1 times negative 1 to the first power over 2 times 1 plus 1, that equals negative 1/3. Okay, that's the first term. The second term is 2/5, right? So for 2/5, I'm going to have, so I'm using the formula here. Okay, so n is 2, so that's 2 times negative 1 squared over 2 times 2 plus 1. And that is going to be positive 2/5. And that's how you get the second term. So Are we okay with that? Are there any, and then you just keep going. So sometimes it helps to write some terms of the sequence out. And the fifth term is -5/11. What are the terms? I mean, if we look at these terms, how they're evolving as n gets greater, what do the terms seem to be approaching? Just using your intuition. What do the terms seem to be approaching? Well, so we're getting some different answers. One student says 0, another person says a half. So there's some differences of opinions. So what we could do is well, we could plot the sequence. Okay, we could plot the sequence. Okay, so we're gonna find out whether this sequence converges or not. But let's plot the sequence. So what I'm going to do, let me stop sharing this for a moment here, and I'm going to go here into the internet. Okay, and let me see here, and I'm sharing with you a website called Desmos. Who has heard of Desmos before? Okay, Kahindi has, Justice has, so Michael, so Eric has, and normally what I would like, of course, you can use your TI calculator can be used to graph sequences. You can put the calculator in what's called sequence mode. If we were in the class, I'd be able to show you this on a projector. There's a mode, like your calculator is probably in function mode. If you go to mode, there's a mode called sequence. So it's on the fourth line. If you click on mode, go down to the fourth line, there's a SEQ feature that if you select that, you get your calculator in sequence mode. But I wanted to just show you Desmos. It actually can be very helpful. So let me just show you what I'm going to do here. So the sequence we're interested in is it's the one we're interested in. It's n times -1 to the nth power over 2 times n plus 1. So what I'm going to do is, and Desmos is new to me. It's new to me. So I'm basically I'm learning, okay, but I'm going here to this number 2 second box here, and I'm going to type in the formula, but it's in terms of an x formula, but that's okay. I'm going to have x times -1 to the x. It's probably like typing answers in WebAssign, divide. Well, hold on. Divided. There we go. And you can do this too. You can bring up Desmos on your computer, okay, on the internet. And there I have this the sequence, okay? I have it. Now what it's going to do is it's going to graph the sequence. And maybe what I'll do here is try to have a little bit better window. So I'll click on the little wrench, and I'm going to let the x-axis go out to maybe 50. Okay. Well, no, let's do 20. So we're going to plot 20 terms of the sequence with a step, and I use the step size of 1. That makes sense because the first term of the sequence, second term of the sequence, third term of the sequence, 20 terms. That makes sense. In the y-axis, I'm going to change that. I'm going to maybe have it go from -1 to 1. I want to have a reasonable window. And step size there, maybe I'll have it be 0.1. Okay, and maybe actually for my x-axis, maybe I'll do 30 terms of the sequence. Okay, and let's see here. Now, all right. So what it's doing is what was the first term? The first term. What was the first term of the? So I don't have I only have the first 10 terms of the sequence, but I'll show you how to get more. Let's just look at the first 10 terms of the sequence. What was the first term? Negative 1/3. Well, that looks about right, right? When n is 1, you look at that dot, it's at negative 1/3. The second term of the sequence was what? Second term was equal to 2/5. Good. Well, 2/5 is 0.4. So, and then the third term of the sequence was negative 3/7. Negative 3/7 is negative 0.42, and that jives at n equals 3. That agrees. The dot's at negative 0.42. Are there any questions so far with what you're seeing in the sequence? Let me know. So Desmos is very popular. It's free. It's very popular, and I know students do use it, and I'm using it here too. All right. Well, if you're good so far, let's see. Now we wanted to do like 30 terms of the sequence. So look what I can do here. This little, see, n equals 11. I want to go out to n equals 30. Okay, look at that. Look at how the sequence behaves. The sequence seems to be oscillating. The odd terms of the sequence are negative. The even terms of the sequence are positive. And what are the terms eventually seem to be bouncing back and forth between? What numbers? What fractions? Okay, Kehinde, that is correct. A half and a negative a half. So the sequence is bouncing back between a half and a negative half. I mean, it's pretty clear. And hey, you know, if you wanted to graph more terms of the sequence, you'd have to go and adjust your window. We could maybe take it out to 50. Okay, and then we could just move the little counter here up to 50. And boy, you know, it looks pretty good. Like it's so definitely as n gets large, the sequence is alternating back and forth approximately between a half and negative half. So let me ask you, does the sequence converge? Does this sequence converge? Well, we're getting different answers. For a sequence to converge, the sequence has to approach just one number in the limit. Does our sequence approach one number in the limit? No, it does not. That's right, Rodrigo, because it's going back and forth between two values. So by plotting the sequence, you can intuitively, sometimes you can a lot of times intuitively get an idea if the sequence converges or not, and if it converges, what might be that value. But for our situation, we don't have a convergent sequence here for sequence A. So to be a little more formal about that, then what you can do to sort of to prove this mathematically is we can just look at the absolute value of the sequence. Okay, we can I mean that well, I want to be careful. We're not going to just, we're not going to, the sequence doesn't have an absolute value. But what I'm doing here is I'm saying clearly a half is an important value, right? Clearly a half is an important value. So if I look at the absolute value of the sequence, then the -1 to the nth power goes away. And you're just left with n over 2n plus 1. Well, how does that behave as n gets large? Well, as n gets large, do you think that little +1 there at the bottom matters much? Does that matter much compared to the n and the 2n? When n is large? No, it doesn't. It definitely does not. So, but we can rewrite the sequence in a different form so you can see that clearly. I can multiply the term of the sequence by 1 over n divided by 1 over n, because that's just equal to 1. And rewrite the sequence then as 1 over 2 plus 1 over n. Well, then the limit of the absolute value of the sequence would be a half. So then we can say, I mean, we graphically saw that a half was important. But then we can say that the odd terms of the sequence converge to -1/2, and the even terms of the sequence converge to +1/2. And therefore, the terms of this sequence, and we can denote a notation of sequence by the brackets with the a sub n. The terms of this sequence therefore do not approach a single number, and so this sequence has to diverge. The sequence has to diverge. Okay. And so on the exam next week for this kind of problem, and I'm still working out the details, you know, but I could ask you to justify why you think the sequence converges or diverges. Justify mathematically, and this would be a mathematical approach, giving your reasoning. Intuitively, you can look at the graph of the sequence, but then mathematically, you would justify it by writing down your explanation. And this would be a mathematical explanation. Let's see, Rodrigo says, is it safe to say if the sequence oscillates, then the sequence will be divergent? Well, not necessarily. Not necessarily. The sequence could oscillate, but still like approach zero. Okay, so like for instance, if you had this kind of sequence here, let's say you had a sequence like this, the nth term equals -1 to the nth power divided by n. Okay, so say you had a sequence -1 to the nth power divided by n. Get that written a little more nicely. I mean, in this case, what's the first term of your sequence going to be? Good, -1. What's the second term of the sequence going to be? Good. Good, Tina. Good, Rodrigo. A half. What's the third term of the sequence going to be? -1/3. Good, Sir Fidel. Good, everybody. Fourth term would be good. So, and we can continue on and on and on. So this sequence is oscillating. What are the terms of the sequence appear to approach as n gets large? They appear to approach 0. So that would be an example of a convergent sequence. Yes, yes. And graphically, if we were to do this in Desmos, would you like to see what it looks like in Desmos? Okay, all right, let me go in there. All right, so I think we've solved this A here. If we go in Desmos, okay, so I'm going to have to alter my formula here. Okay, so I got -1 raised to the x power divided by x. So that's the same as -1, and there you go. There you go. There's the first 50 terms of the sequence. And if we want, we can be the x-axis. Let's see, why don't we go out hundred terms. Okay, well, so you see it looks like the sequence is converging to 0. How many think this is pretty cool? Yeah, good. Tina likes it, Candy likes it. Yeah, and so important, so important. All right, well, let's move on then. Let's move on. So again, it's Desmos. All you need to do is go into Google and type Desmos, and you'll get a thing to click on, and it'll come up. All right, so moving on. Okay, now we go to this sequence here in B. So, of course, the interesting part is this 2/10 raised to the nth power. Okay. Now we could plot that sequence in Desmos, but we can also write out a few terms, and that's what I do here. I write out some terms. So the first term is 3 minus 0.2 to the first power. Second term is 3 minus 0.2 squared. Third term is 3 minus 0.2 cubed. What seems to be happening to this portion of the sequence as n gets larger? Looking at the values here. Yeah, the term that 0.2 to the nth power is going, 0.2, 0.04, 0.008. That 0.2 to the nth power appears to be approaching what? As n gets large. It appears to be approaching 0. Hence, That's right, Tina. And so, you know, I wrote down the values of the first three terms. The sequence appears to converge to 3. And so, therefore, this sequence converges to 3. All right, it's a convergent sequence. All right, are there any questions on that? All right. Well, may I move on to the next to the sequence C? Are there any? Is everybody good here? All right, all right. See, in the classroom, if you were face-to-face class, I could look at you all and tell if we were ready to move to the next problem, you know, because I'd see people are done copying the notes and so forth. So, you know, on that. So, but here I have to ask. Okay, let's go to C. So, you know, sometimes, I mean, a lot of times you don't have to plot the sequence. You can just use your intuition. So for this third sequence, we have the tangent of the angle given by 2n pi over 1 plus 8n. So let me ask you, what the 2n pi over 1 plus 8n, what's kind of the nuisance part of that angle? What's kind of the nuisance part? I guess what I'm asking is, well, yeah, if I say too much, I'd be giving it away. But let me ask you this: when n gets large, does that 1 there in the denominator affect things? In other words, when n is large, the angle, is it affected much by that 1? No. So the answer is no. As a matter of fact, when n is large, we could almost ignore that 1, you know, and really focus on the 2n pi over 8n. Okay, well, what is 2n pi over 8n? What happened? So we can't like simplify the n's because we do have the 1 there. But when n is large, that's right, Candy, that's right, Tina, that angle is going to approach pi over 4. We can formally show that again with the work. So we don't have to run to Desmos and plot that sequence. We can use our intuition here. So, all right, what I'm going to do is I'm going to rewrite the angle. I'm going to rewrite the angle by multiplying by 1 over n on the top and the bottom. And when I do that, the angle is going to become 2 pi divided by 1 over n plus 8. And remember, I'm going to let n to determine if the sequence converges. I have to let n goes to infinity. I have to let n get big. And what's going to happen to this angle? Well, what happens to 1 over n as n gets large? What does 1 over n approach? It goes to 0. And so you're going to get, when you then take the limit, you're going to get the tangent of 2 pi over 8. Thank you, Rodrigo. And you know, the tangent of 2 pi over 8 is pi over 4. The tangent of pi over 4 is 1. And so our sequence will converge to 1. How many like using their intuition a little bit? Yeah, you want to approach sequences from all angles. Now, I think it's good to try to use your intuition, and work, like, show, use your intuition, justify your answer mathematically, and then you can confirm it in Desmos. There are a few problems you're going to see in your homework, in say 8.1. The last couple problems, it says plot the sequence, because the sequences are a little bit hard to work with. But but then it says, hey, confirm it, prove your result. So what I'm doing here is I'm proving the result. And again, your exam next week, you could be asked to, prove the results for the sequence. And so you want to get used to doing that. Are there any questions before we move to the next one? Okay, well, let's move to sequence D. Okay, so sequence D. Oh, wow. Look at this sequence. What do those exclamation marks mean? Factorials. Those are factorials. So I think, do you remember factorials, like 0 factorial is defined to be 1. 1 factorial equals 1. 2 factorial is 2 times 1. So 2 factorial is 2. 3 factorial, hold on here, let me use 3 factorial is 3 times 2 times 1, which is 6. And you can keep going. How many have seen factorials before? You can just keep going. Okay, Michael has. I would hope all of you would have, but maybe who has not seen factorials before? Okay, Rodrigo remembers. And okay, Justice might be the first time for Justice. Okay. All right. Well, n factorial would be n. Okay, n factorial. If we look at how how the factorials are done, 3 factorial is 3 times 2 times 1. What would n factorial be? Like n factorial is so 3 factorial. Let's use that as kind of our example. 3 factorial is 3 times 2 times 1. Okay, so n factorial would be n times what would the next term have to be? Okay, that's right, Tina. N minus 1, and then what would the next term be? Okay, that's right, Michael. That's right, Rodrigo. N minus 2. And then you just keep going all the way down till, what would the last 2 terms be? You you end it with 2 times 1. Right. So that's how you define n factorial. Okay. 4 factorial. Tyreek's asking about 4 factorial. 4 factorial would be 4 times 3 times 2. Let's try to make that look good. 4 times 3 times 2 times 1, which is 24. All right, Tyreek? All right. So how are we going to handle this problem? How are we going to handle this one? This might be, well, what'll happen, Tyreek, is a huge number. Like if you try to put in 100, like your calculator has a factorial button. If you go to the math button, third row down, math, and then go over to PRB for probability, there's the fourth selection is a factorial sign. That's that exclamation mark. So if you try to put in like 100 factorial, your calculator won't be able to handle that. The number's too big. But we're gonna so see, like this problem, Desmos might not be able to handle because the factorials get very large. I mean, astronomically large. But using our intuition, we can, and our knowledge of the factorial, we can work the problem out. Because what I've done, just for your reference, is above here, I've written the first 2 terms of the sequence. And you can see like the second term of the sequence has 9 factorial. 9 factorial is actually 362,880. That's in that denominator. So this would be kind of a mess to do. This might be difficult to do in Desmos because well, you see, Desmos would have to calculate these big factorials, and I'm not sure it can do that, to be honest. But it's okay. We don't need Desmos for this. We don't need to graph these sequences here, because look what I do. All right, I'm going to take the limit of the nth term as n goes to infinity. But what I'm going to do is I'm going to leave 4n minus 1 factorial alone. But I'm going to write out 4n plus 1 factorial. I'm going to write out the 4n plus 1 factorial. So 4n plus 1 factorial. This is where I'm focused. 4n plus 1 factorial. So the first term is 4n plus 1. So if I write 4n plus 1 factorial out, okay, the quantity 4n plus 1 factorial. The first term is 4n plus 1. The second term is 4n. It's 1 less. And then the next term would be 1 less than that, 4n minus 1. And then the next term would be 1 less than that, 4n minus 2, all the way down to 3 times 2 times 1. But 4n minus 1 times 4n minus 2 times, you just keep multiplying until you get to 3 times 2 times 1. All that can be expressed as 4n minus 1 factorial. You see that? And so what's going to happen is you have a 4n minus 1 factorial in the denominator and a 4n minus 1 factorial in the numerator. So what's going to happen is they simplify out, they divide out, and so you're going to get the limit of 1 over 4n plus 1 times 4n in the denominator. And so this sequence will approach 0. Absolutely fascinating. So you have to be careful on these kind of problems, because like for for multiple choice problems. I'm trying to recall. I think the problems in your homework, though, you type in the answer. But you know, but the sequence converges to 0. Hey, how many like factorial problems? I think they're kind of cool. Uh-oh. Tina doesn't like them a whole lot. Michael does. Well, you're going to see them later on when we do Taylor polynomials, the Taylor series. Tina says, how did the denominator become those 3 terms again? So what, like, good question. So I think here's how I'll phrase it. So 4n plus 1 factorial. Do you agree, Tina, that can be written as 4n plus 1 times 4n times 4n minus 1 times 4n minus 2 all the way down to 3 times 2 times 1? Could it be written as this product here that I'm circling in blue? So 4n plus 1 factorial. Can I write that this way? Yes. So what I'm doing is then this part here, the 4n minus 1 times 4n minus 2 times 4n minus 3 times dot 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 times, you keep going and dot 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 3 times 2 times 1. The dots mean you're just multiplying terms in the middle there. That expression can be written as 4n minus 1 factorial. And so then the 4n minus 1 factorial terms will simplify out. Okay, does that are you comfortable with that? All right, good. That's right, Rodrigo. Rodrigo's saying he has this is like not part of the proof here, but like, yeah, if you had 4 factorial is 4 times 3 times 2 times 1. But 3 times 2 times 1 is 3 factorial. So 4 factorial is the same as 4 times 3 factorial. Absolutely. And we did the same kind of thinking here so that we could get a simplified answer. Very good, very good. All right, are there any questions at all before we move to the next problem? Okay, well, let's move to E, sequence E. Okay, so I'm trying to do, the book has some nice examples. I'm trying to do some additional examples for you. So, wow, look at this sequence. Look at this sequence here. The sequence is equal to 2 times the square root of n times the sine of pi over the square root of n. So if you saw this problem, what might, let's say you're looking at it homework, what's the first thing you might do for that sequence? Maybe to give you an intuitive feel. Okay, So Michael says write out the table. In other words, we could list some values, but also could we plot the sequence? This sequence might be one that's nice to plot in Desmos. Yeah, I mean, we always like to use our intuition if we can. What I mean is, we always like to, if we can mathematically, look at it and and intuitively get it that way, that's good. But why don't this one we look at Desmos? So, all right, let's bring up Desmos. Okay, and what I'll do here is I'll just well, I'm not sure about my window. Let me go ahead and type this in. We have 2 times, let's see, I need the square root. Okay, good. I was hoping if I just typed SQRT, it would give it. So it works a lot like WebAssign in terms of things. I just typed PI. Really pretty cool. Okay, so I got 2 times the square root of x times the sine of pi over root x. Okay, and let me see here. So have it in there, and doesn't look like it doesn't look like it's plotting the sequence. But is that true? Is that true? Horizontal axis gives me 100 terms. What might we have to do for this sequence? What might we have to do? Adjust the size. Good, Michael. Adjust the window. Okay, that's what I'm going to do. So, okay, I'm going to go to where the wrench is, the graph settings. And I like the x-axis as it is, but the y-axis, well, maybe I'll go from, like maybe the calculator. The standard window is, negative 10 to 10 on the y-axis. So maybe I'll try that. With a step size of 1. That worked pretty well. That worked pretty well. Now I don't even need, really, I can even do it better. It looks like I'm not really going to need, well, maybe I'll, go from negative 1 to 10. So, and notice it's in radians. Gotta have it in radians. Okay, so what does this look like the sequence is approaching as n gets large? I wonder if okay, look, I can touch the dots. I can touch the dots. And I touch the dot and I get 6.176. I'm not quite happy with that. I'm gonna go out. I want to go out maybe 1,000 terms. The sequence. Let me see here. I want to take it out further. Well, let me see. Maybe 500. Okay. And let's see. For n, I got to take it out. Can I just, okay, here, I can change it right here. Pretty cool. Pretty cool. The dots are very close together. It almost looks like a continuous function now. Maybe, let me go out to, let me try 200. I kind of like to see a little separation between the dots, so I'm just playing around a little bit here. I don't know if the dot size can be adjusted. I got kind of big fat dots here, but this is okay. So at 200, I'm getting 6.231. Now, do you think if you type, so if I said that does the sequence appear to converge? Does the sequence appear to converge? It looks very positive. But if I were to type 6.231, like let's say, like WebAssign says, if the sequence converges, write the value it converges to. If I wrote 6.231, you think WebAssign will mark it correct? No, it will not. I mean, you know, it's close, but not good enough. So we're going to have to, so we do have an idea that the sequence converges, but we got to find the exact value it converges to. So let's go back into, well, are there any questions so far? All right. Let's go back in here to then back to the we're going to use an old friend here. Okay, we're going to use L'Hopital's rule. How many remember L'Hopital? L'Hopital's rule. Uh-oh. I'd like to at least get maybe one response. Okay, Rodrigo remembers it. Okay. Well, so look, here's what I do, okay? All right. Tina remembers. So you have, what I'm going to do is I'm going to look at the limit so L'Hopital's rule applies to functions. L'Hopital's rule applies to functions. So I'm gonna say, okay, let my function f of x be 2 times the square root of x times the sine of pi over root x. Okay, now if I can find the limit of this function and find out what that limit is, the sequence will approach the same limit because the sequence takes on the values of the function just though for when x is integers. But if the function approaches a limit, the sequence will approach that same limit. So what I do is I rewrite the function. First of all, I write the square root of x is x to the half, and then I bring the I write the function this way. Okay, I write the function that way. So it's like multiplying, think of like multiplying the function by x to the negative half over x to the negative a half. And then that'll get me here. But the numerator and denominator, as x gets large, both approach 0. Okay, the square root of x goes to infinity, so in the denominator, 1 over the square root of infinity is 0. And then in the numerator, the angle pi over the square root of x, as x gets large, that's going to approach 0, that angle, and the sine of 0 is 0. So you have to use L'Hopital's rule. Okay, and so I have the little h here, meaning I'm going to apply L'Hopital's rule. We have an indeterminate form of 0 over 0. I'm applying L'Hopital's rule. And so I take the derivative of the numerator and the denominator. Here's the derivative of the numerator. Got to use the chain rule, of course. And then here's the derivative of the denominator. Do any nice things happen here? Right, cancellation or simplification. And I think it's good actually that I hope most of you are following me like on the screen. I guess when I share a document is you're able to like see the notes and work ahead, but I think it's good not to work ahead. I think it's good just to follow me on the screen here, just like it were, you're in class. And so, okay, we're going to get 2 times the limit as x approaches infinity of pi times the cosine of pi over the square root of x. Okay, and then, well, the cosine of pi over, pi over the square root of x as x gets large, that's going to go to 0. And the cosine of 0 is 1. So, I mean, I could add a little intermediate step here. I could say this equals 2 times pi times the cosine of 0. Right? And the cosine of 0 is 1. So you get 2 pi. Therefore, the sequence converges to 2 pi as well. If the function approaches 2 pi, if the limit of the function equals 2 pi, the limit of the sequence will naturally equal 2 pi as well. And you see, WebAssign would want you to type in 2 pi. That's what it would want. So you see, you're never, I mean, unless you, well, that's what it wants. So why didn't the pi get canceled? Surfiel asks. Well, let me see here. So here you have the pi right here, but what would you, is that the step you're talking about, Surfiel? Okay, all right, good, good, good. All right, are there any other questions? The book, of course, the book is a little more formal in terms of like, there are, certain theorems, like this is actually a theorem that we apply, that if the limit of the function approaches a limit, then the sequence will approach that same limit. That's theorem 2 in the textbook. And so, the book is can be a little formal with theorems. We're just, intuitively it makes sense. I'm definitely an intuition guy. And what I mean is, anytime I can use my intuition, I like to use it. And that's helpful for the 200 level math courses as well. And I'll be teaching some of those in the spring. Incidentally, are you able to register for courses now? Are you able to, is registration open yet? Not yet, okay, all right. In November then, November 9th, okay, Cologne, very good. Is it visible, the schedule? Is the schedule visible to you for the spring? Surfiel thinks November 2nd you register. Oh, okay, if you have early. So you'll so you have early registration. If you have enough credits, I guess you can register more early than other students. But but somebody said the schedule is visible. Okay, great. Okay, let's move on. Let's get that last. Let's look at the last one. Okay, so here All right, now that is an interesting sequence. Negative 3 to the nth power divided by n factorial. Okay, so I'm going to just show you. So we could try to plot that in Desmos. I'm not sure. Let's see if Desmos. I'm not sure. I'm just looking here if it has factorial capability. You'd have to investigate that. I'm not sure if it does, but I'm going to show you how to do this one. I saved the hardest one for last. All right, what you're going to do is you're going to look at the absolute value of the sequence. So this is just like the first sequence we looked at. First sequence we looked at the absolute value of the sequence. And then, you know, because we don't want to worry about the oscillation behavior right now. So the absolute value of this sequence would give you then 3 to the nth power over n factorial. And we're going to study how 3 to the nth power over n factorial behaves. And then we'll go back to our original sequence, negative 3 to the nth power over n factorial. So we're going to use something here called the squeeze theorem. How many remember the squeeze theorem from Calculus 1? All right, Justice remembers it. Tina remembers it. Sure. Eric remembers it. All right, we can use the squeeze theorem here, mostly for Coulomb. And what I'm going to do is I know that the absolute value of my sequence is going to be greater than 0 for sure. It's greater than 0, and I write out the sequence this way. So for n greater than or equal to 2, if I want to write out this sequence 3 to the nth power over n factorial, I could write that as 3 over 1 times 3 over 2 times 3 over 3 times 3 over 4. Okay, keep going, and then the last terms would be 3 over n minus 1 times 3 over n. Now in this case, what I'm doing is I'm writing n factorial as 1 times 2 times 3 times 4, and you keep going, and then the last terms are n minus 1 times n. So that's equivalent to like taking 4 factorial and writing it as 1 times 2 times 3 times 4. Right? We can do that. We can do that with factorial. So 4 factorial we had written before was 4 times 3 times 2 times 1. But hey, you can write 4 factorial as 1 times 2 times 3 times 4. So all I did was the n factorial there in the denominator is 1 times 2 times 3 times 4 times, and then all the way up to n minus 1 times n. And then in the numerator, I keep repeating the 3. But then I'll notice that this sequence is going to be this sequence is less than or equal when n is greater than 2. If you for that, it's the sequence will be the I'll say this the right way. The term of the sequence will be less than or equal to 3 times 1, because you have that there, right? Times 3 times 2. Okay. And then, hold on here, one moment. One moment. Just checking one thing out here. Right, and then times 3, and there, in other words, there are three terms here, 3 terms. So the reason I can say that is, you see, this part of the product, the 3 over 3 times 3 over 4, all the way up to 3 over n minus 1, that is less than or equal to, hold on, I'm going to write that properly. That product is less than or equal to 1. Right? At highest, it would be 1 if you just had 3 over 3. That would be if you were, you know, the third term of the sequence. But it's going to be less than or equal to 1. And so this is true. But this simplifies to 27 over 2n. So for n then, for n greater than 2, the nth term of our sequence, okay, the nth term of our sequence, the absolute value of the nth term of the sequence, is going to be less than or equal to 27 over 2n. But as n goes to infinity, the limit of 27 over 2n on the right side here, on the right side, that is going to equal 0. And so by the squeeze theorem, the sequence the absolute value of the sequence has to approach 0 as n approaches infinity as well. Because the sequence is bounded, it's bounded below by 0, right here, and it's bounded above by this 27 over 2n. But 27 over 2n, as n gets large, it approaches 0, meaning that the sequence, the absolute value of the sequence, the term of the sequence, as n gets large, has nowhere to go. It's has to approach 0. So the sequence will converge to 0. And that's how that works. That's how that works. Okay, and so one moment here. And so the sequence converges to 0. Squeeze theorem. How many think that's kind of cool? All right, not too many big fans here. That's okay. But that's how sequences, you know, that you see a lot of examples now of different sequences and how to work with the different sequences. You've seen a lot of examples. So what I'd like to do is, if there are no questions, I'll stop the recording.